用吧，
用啊，我没有手拿，因为我要写。我们天山里面。
要做那个。不要看着我笑。Good evening, everyone. It's 7:30 already. We are going to start our seminar. And as I mentioned before, we welcome Dr. Kising to have a few words before we start our seminar.
Okay, thank you for the organizer. Thank you for coming to today's reading seminar here. So this seminar is actually try to stimulate or motivate students to study on advanced topics. Here. So this is a student-initiated program here. I was just guiding them. Okay, I didn't do much. So I want to create a free learning, free study environment here, learning environment here, so that people can discuss, maybe criticize, okay, criticize, yeah, sure, but not in a bad way, okay, it's not in a bad way, but discuss, discuss about new ideas, yeah, that's all. We could even come up with a new research topic even, if you like, yeah. So also thanks for the faculty members who come. Yeah, we have Yan Kang here from physics, Yan Kang, Yufeng, and then Ian from Max also. Ian, right? Yeah. Okay, yeah. So we hope that there are more faculty members that could join, and maybe we could have future reading seminar also on various topics, different topics, as long as any faculty member wish to lead these students. Yeah. So it'll be good for FYPs, masters, or even PhD. Okay, for future. So today we will have Ryan here. So Ryan is our PhD student. Right, just started, right? Okay, he graduated as a master here under Darren, and starting PhD with Yajin. Yeah. So we will have him maybe for 2 weeks. Again, next week also him. Okay. Yeah. So he will tell us some topics on algebraic geometry, starting with Hilbert Nullstellensatz. Okay, the famous theorem in algebraic geometry. And if you don't feel asleep, so we have rest, right? We have a break in 1 minute, in 1 hour, sorry. 1 hour. So if you don't get sleep in 1 hour, right? So there will be a snack for you here, so to keep you awake. So there's a Penang snack here. You can
Not stack.
not snack. This year is a snack year. So we just pass the Chinese New Year. Yeah, SNS. CK, huh? Yeah. Yeah. Hello. Yeah, so this actually this event mostly initiated by the Algebra 1 student group theory, and we have help from 2, 3, what? 2, 3. You guys are 2, 309. So yeah, 2304 here. So this class actually mostly target those who take group theory before. Okay, after group theory, you can do it. But even if you haven't done group theory yet, you are welcome to come. So maybe you need to self-study more. Okay, we have material put on the Teams, right? So weekly we will update, okay, whatever we have put on the board, and whatever we discuss, we will try and document it. Okay, so that everyone can benefit from the discussion. And is it okay? Hand or not, speaker? Can you commit? Okay. Okay, cool. So we'll start.
Okay, so I'm Ryan. I'm actually pretty nervous because the audience is a bit larger than what we expected, but it's a very positive start to go with, and let's hope that the numbers do not decrease over 5 weeks, because that's usually the case, even in proper classes, right? So okay, so basically today's agenda is to basically just is to present the key ideas that form this subject in mathematics. So namely the Hilbert Nullstellensatz. So which says that to study algebraic varieties, we just need to study certain types of ideals of polynomial rings. Okay, so that's the goal for today. Okay, so yeah, and this is the theorem that really gives rise to the two words algebraic geometry in some sense. Okay, so but a bit even before technicalities, in a nutshell, algebraic geometry is actually just simply the study of zeros of polynomials, roots of polynomial equations. It all started from there. Okay, so as we go on, we'll see some examples. What should I say now? Okay, so just a little bit of admin, just doing this very quick one. So actually, we have Dr. Keesing actually suggested this textbook for us to this as a main textbook for us to refer to, which is Algebraic Geometry by James Milne. It's online. It's in. We actually have a Teams channel. So if those of you want to join, please come and find Reshwa, the first guy here. So he'll add you to Teams, and then or if not, you can just download this book online. It's on Milne's website basically. So this is the if you see the topics for the 5 weeks that we've designed is mainly from this book. But at least for my part, I don't really follow this book. I follow a more classical and a more notorious book, the famous Yellow Book by Robin Hartshorne. And okay, but I also don't follow that fully, but because I learned from that book about half a year ago, so that's why my part is a bit based on my notes that I did back then. Okay, but and by the way, this is not a lecture, so I hope I'm not the one just presenting for 2 hours. So if you have any questions, you can stop me anytime. And And we'll see how to discuss things also on the spot. It's more meant to be like a flipped classroom or discussion session more than a lecture, actually. So, and of course, I'm not an expert. I'm not an expert in this field, so there may be things that I've said wrong. So there are experts in this room, so I'm also learning from you. So anything wrong, just shout out, okay? Okay, so just as an intro, so you've probably heard of the words classical and modern algebraic geometry. And so our reading course is a bit more on the classical side. So meaning we're mainly doing affine spaces, affine varieties, and projective varieties. Mainly just that. So it's more on the classical side. So we're not doing anything about sheaves or schemes. Those are what we call modern algebraic geometry. Meaning if you read papers nowadays on geometry, you see languages from here, but you won't see that in these 5 weeks because it's too abstract. Okay. And I haven't learned that myself either, but at some point I'll have to learn the language for my research. Okay, so we are basically focusing on the classical treatment here. Okay, and next semester, math department is offering classical algebraic geometry. It's also classical. It's not modern. Okay, so that's a very brief history here. So as we said, algebraic geometry is basically the study of zeros of polynomials, right? So that's what we'll start with. So we're not wasting too much time. Let's get into the math. Okay, so we start with a definition, as usual, the math way. So I want to define what is a zero set. So, before that, we have to tell you what is affine n space. So the setting here is, let big K be a field. In this case, at this moment, we let it to be any field first. So in the context of algebraic geometry, usually we assume our field to be algebraically closed. So let's say if you don't know abstract fields, just think of complex numbers for now. So basically our prototype is geometry over complex numbers. Okay, but just to define affine space, we can define affine space over real numbers also. So I don't make that restriction here. Later on, as we progress up, we'll say why we like our fields to be algebraically closed. Hold on. Meaning algebraically closed, meaning that every polynomial with coefficients from complex numbers has a root, right? You learn that. You know that from year 1, fundamental theorem of algebra. But if our polynomial is over real numbers, and we find roots in zeros in real numbers, x squared plus 1 equals to 0 has no root, right? So these are the kind of issues that we're looking at. So that's why usually we assume to be algebraic closed. So just think of it as complex. We are doing polynomials over complex numbers. So coefficients are complex numbers, and we find zeros that are complex numbers. Okay. So now I have to tell you what is affine n space. So affine n space over the field K is denoted by both face A for affine, and then we have a dimension n. This definition of a dimension is, for now, let's just abuse the language. And then in week 3, I think, right? Week 3, we'll have a special topic on what is the dimension of affine space. What is the dimension of an affine variety? That'll be the technical part there. But for now, just say so over is as we all a base field, so let's denote it like that. But as a set, it's actually just Kn. So it's like n copies of complex numbers that kind. C or basically Cn. Just think of it as Cn. Okay, Cn. So the elements of affine space just look like as a set is the same as Cn. So it's like it will look like A1, A2 through AN, where all your entries are from the field. Okay, as a set is just Kn. But why do we give a fancy new symbol and a fancy name called affine n space over the field K? Is because when we talk about Kn, for example, Rn or Cn, you usually think of it as vector spaces, right? As a vector space. So you think of it as it has a zero vector, it has an origin, right? So the notion of affine actually means that we don't care about the concept of origin. So that's why some people say that affine space is basically Euclidean space without origin, that kind of thing. Okay, so meaning that the origin is nothing special in the context of affine space. But as I said, it's still the same place. It's the same space. Okay, so that's just the intuition here. Okay, so because we are finding the zeros of polynomials in affine space. Okay, so if it's affine n space of dimension n, that means we'll be talking about polynomials in n variables, that kind of thing. Okay, so the complex thing is basically just A1C. Okay, so basically, if you know that your complex numbers is in affine space, I guess it's just A1 because it's one dimensional and it's over complex numbers. That kind of thing. Okay, so let's start with the definition of a zero set. So okay, so we start with a set, be a non-empty subset of the polynomial ring K polynomials in n variables. Okay, so basically this set S is a set of polynomials in n variables, that's all. Okay, then we define the zero set of S. We denote it by VS. In a moment we'll say what that V means. So it's a set of all points in AN that kills all polynomials in this set S. Okay, so it's all the points, let's call it points X in AN. I'll stop mentioning K here, okay? So just think of K as an algebraically closed field. So for example, complex numbers, just think of it as C actually. So just think of these as complex numbers, n tuples of complex numbers, such that f of x is 0 for all polynomials f in S. Okay, so the zero set of S is just the common roots of all these polynomials in S. So with a definition, let's do some examples so you can feel the definition. So let's say S contains the polynomial, let's say x squared minus 1. Let's say it contains let's say it just contains one polynomial. Okay? And we treat this polynomial as a polynomial with coefficients in complex numbers in one variable. Okay, so you know how to solve this polynomial already, right? So what are the zeros of these polynomials? So what's the zero set of S, meaning what are the points X in A1, which basically is complex numbers, where X squared minus 1 is equal to 0, right? That's the definition of zero set. So meaning you just solve this thing like secondary school. So you get 2 points plus minus 1. Right? So the zero set of this polynomial is a set with 2 points on the complex plane. So if you like pictures, it's just your Argand diagram. Just your Argand diagram with 2 points. Point here, point here. So these points form your VS. Okay? This is a very simple example. Then, of course, you can have sets with more than one variable, more than one polynomial. So let's do something like x squared minus 1, and let's fork up something. So let's say x squared minus 3x plus 2. Let's say, okay? So the zero set, now the zero set will be what? It has to be a zero of both of these polynomials, right? So it's all the complex numbers such that both polynomials have to be 0. Right? So I'll skip details. So here you get plus minus 1, right? So, and then here you get 1 and 2, right? So what's the common? What is the zero set here? So in this case, our zero set just contains 1.1. Okay? Minus 1 is not in this zero set because it doesn't satisfy the x squared minus 3x plus 2. And then 2 is also not part of this zero set because it doesn't satisfy x squared minus 1. Okay? So that's the so if at this moment, most of you will just feel that this is just reformulating high school algebra in a more fancier language, right? And yes, and actually in some sense, this is the life of a math major, right? So it's normal. Okay, so now we've done zero sets. Okay, so then now you have a few zero sets, then now I can introduce a new fancy term to you. So let's say also, by the way, it's obvious that the zero set is a subset of affine space A and K. Okay. So now I want to tell you what is an algebraic set, or more specifically, affine algebraic set. So we say that a subset can be empty now. We allow empty sets. A subset A, let's say a subset A of affine space is called an affine algebraic set. Yeah. Oh. Okay. Actually, I just mentioned it just now. Affine. Actually, do you recall me mentioning we talk about Kn as a vector space, right? right? So the word affine, for now, you just think of it as we forget about the origin. That means we forgot about the concept of origin. We forget about the concept of distance and angles. So that's what the word affine means. So it's actually really the same space, but you just forget some structure, that kind of thing. That's what mathematicians love to do. Forgetful functors kind of ideas, right? Okay. Does that answer your question? Yeah. Okay. Okay, so an affine algebraic set is basically as a subset of affine space is an algebraic set if it is the zero set of some polynomials. That's all. Okay, so an affine subset is algebraic if there exists some subset of the polynomial ring. So always, because we're in n space, so our polynomial ring will be in n variables, such that A is equal to V of S. So this is the way we state in math. In math language, it's stated like that. But in English, it just means that an affine subset is said to be an algebraic set if that set contains all the zeros of some polynomials, are exactly the zeros of certain polynomials. Okay. So these two examples we did just now are algebraic sets. Okay. All zero sets are all zero sets algebraic. Zero sets. If it's a zero set, yep, by definition, that's all. Yeah. Oh, okay. Okay, let's see. Yeah, that's not possibly be a zero set. If we're in algebraic closed field, then it's more difficult. But let's say
if n equals 1,
yeah.
and every algebraic set is either finite or cofinite. It's cofinite, it's fine. So
Yeah. Oh yeah, actually we have that as an example. We'll work that out later. Yeah, you're talking about A1, right?
yeah.
A1. Okay. Okay, then maybe let's bring that forward. Because I think I plan it to put it somewhere later. But let's move that forward anyway. Oh yeah, because I put it in the Zariski topology part. Okay, so let's bring that forward. So as Dr. Yan said, let's talk about A1 over complex numbers. So the question here is, what are the algebraic sets in A1 or in over C? Okay, so okay, hold on. See, oh, the way I did it is a bit different. So yeah, okay, so let's say we have the zero sets. Okay, because I actually use some result that I have to present first. So okay, let me postpone this example again. Let me state some basic results of zero sets. First, we'll use some of them to explain this example in more detail.
And this one is to describe a subset.
Yeah. My guess is that if we're over an algebraically closed field, then you can always take the monomials and generate. Yeah. Yeah. It's the other way around. Yeah. Yeah, sometimes I also like kind of somehow ignore these kind of questions, so it's quite good. Yeah. Yeah, otherwise why like King said, why two words for the same thing? So maybe later we can figure out like in what case we can find an affine subset that is not a zero set. Yeah. 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 Okay. So now I want to move the properties. So we want to talk about properties of zero sets, of algebraic sets actually. So, okay. So first property is what we call, there's inclusion reversing, or those of you who know language of categories, it means contravariant. So it means that V is a contravariant functor. Fancy language again. Those who don't understand, just forget about it. Okay, so inclusion, it just means inclusion reversing, meaning that if we have affine set, if we have two subsets contain of the polynomial ring contained in one another, then their zero sets, the containment of their zero sets are in the opposite direction. Okay, it's quite intuitive. The intuition is very easy. So the intuition is just like, with more polynomials, it's more difficult to find common zeros, that kind of intuition. So with zeros, there are less points that satisfy more polynomials. So that zero set is smaller. That kind of idea. Okay. Yeah.
Just write sign or something.
What?
VS is greater than and equal to VT. If I'm not.
If T contains S, then VS contains VT. Okay. Or if you're not comfortable with this flip, then I'll write VT is contained in VS. Yeah, is that what you mean? Yeah. So the meaning is that T is the bigger set, right? T is the bigger set than S, right? So the zero, so meaning T contains more polynomials than S. So for example, T, you can look at the example we did just now. So, so maybe like, let's call our second example T. Then you get the picture. This is an example that you can feel. Okay, so T has two polynomials, S has just one polynomial. So now T you have to satisfy, you have to find common roots of two polynomials. But for the first case, as long as you satisfy that polynomial, because the set has only one polynomial. So whatever zeros of that is in the zero set. But for T, no. So you can see that, so in this case, you can see that T contains S, right? But Vs contains Vt. So that's why we say it's inclusion reversing. Okay? So meaning you take, it's like S subset of T, then you take V on both sides, take the zero set of both sides, you have to flip the inclusion. Okay? So that's the main property. So this is basically, we have already done one small part of Hilbert Nullstellensatz. Okay? Okay, so that's the first property. And I think because of time constraints, I think we'll skip a lot of proofs today. Okay, so second thing is that, let's say, again, if S and T are polynomial sets, and then T is the ideal generated by S. Okay? Then the zero set of T and the zero set of S are the same thing. So what does this mean? This means just like let's look back at one of these examples. So let's look at the simple example S with one polynomial. Okay, so S contains one polynomial. So then what is the ideal generated by? What's the ideal generated by S? So it's the principal ideal. I should write it down. So in that example, so let's say S is this set, and then T, so T will be the principal ideal generated by this polynomial, right? So those of you who haven't learned ring theory, it just means that these are all the multiples of that polynomial. Okay. So certainly, T is the largest set, right? But it's all multiples of x squared minus 1. So of course, what happens to this part is not important. Everything here that gets skewed. So everything there belongs to the zero set. Okay, so taking multiples of x squared minus, in other words, taking multiples of x squared minus 1 does not give us more zeros. Okay, that's the intuition. Yeah. Mm. Did I define my ideal wrongly? Oh, okay, yeah. Oh, yeah, this one. Too general here. Thank you. And actually, I don't even need K here. Let's just get K to be C. Yeah.
So S can also be infinite.
Yeah. For example, T is an infinite set, right? Yeah. But they give you the same zero set as S. Okay. This is one of the important building blocks as well. Okay. Now, okay, now we have two more properties, but it's basically leading to Zariski topology actually. So, but let's forget about topology language first. I just want to say, just think of it as what is the intersection of zero sets? Let's say we have a collection of sets S alpha. So we should say let this indexed by J, let S alpha be a collection of non-empty subsets of polynomial ring. Then what's the intersection of these zero sets? Think about it. You can think intuitively. It's quite intuitive also. So okay, so the intersection of zero sets is basically the zero set of their union. You get the picture here? This is in abstract language, but the picture is, again, you can look at that two examples. So let's say you have a, let's say you have a, let's say we have this example. So I ask you, what is the intersection of these two zero sets? What is ZS intersect ZT? Get the picture here? Yeah. So it means ZS means zeros of polynomials from S. So it's zeros of x squared minus 1. ZT is what? The zeros of x squared minus 3x plus 2. Yeah. Oh yeah. Yeah, I get confused sometimes. Yeah, because the V, because later next week will say the V actually stands for like, there are two ways they say what the V stands for. The Z here means zero set, so that's why I'm used to this notation. Yeah, some books write V, some books write S. The V actually stands for variety. That's one way. The other way they say that V stands for vanishing. So that's another way. Okay, so what's V? So what's VS intersect VT? Right. So you know it's one, right? Then we don't need to know whether it's one or not. So just think of it. VS is the zeros that satisfy everything in S. VT are the zeros that satisfy everything in T. So you intersect them means what? These zeros the zeros satisfy both things in both S and T, right? So that's why it corresponds to the zero set of the union. Get the idea? This is the intuitive. I'm not doing things rigorously, but this is the intuitive idea to think about these concepts. All good? Okay, so one more, then we can move on to ideals. Maybe a bit slow. Okay, now, so how many of you know general topology? Okay, okay. Then how many of you know open sets and closed sets? A bit more. Okay. Okay, so basically basically what we've just said is that it's kind of like saying that arbitrary intersection of closed sets is closed. Okay, we'll do that next. We'll do that in more detail. We'll translate this into topology next week. Okay, then so now those of you who know topology know what's coming up next. We want to talk about what the union of zero sets. But now our union has to be finite. Okay, so you think about it, now we have to take common zeros of S and T. So when you put the polynomials together, it's actually the zero set of the union of those polynomials. Right? That was part 3. Now for part 4, what are we looking at? So what happens if how do you combine all the zeros together? Right? How do you unite all the zeros together? Right? SIs are polynomials, are sets of polynomials. Then we have to take the union of all the zeros. So how do you combine them together? I heard some answers just now. Did someone say something? A good guess, but no. Intersection mixed. Intersection of the polynomials. It's a good guess, but no. I heard the correct answer. I don't know who. The answer is to take all the products. So meaning that again, let's use back this example. So what is VS union VT here? So it's just so now you know if you want to write out explicitly, it's -1, 1, and 2, right? 3 points. So how do you find a set of polynomials that has all these 3 as roots? So the obvious way is just multiply them together, right? So it's V of ST. So this set the product of sets notation is just like, it's just things of all the forms that of the product of what of a polynomial from S and a polynomial from T. Okay. Does that make sense so far? So these are the basic properties of zero sets. So in some sense, we've almost done half of Hilbert's Nullstellensatz. Okay, so now the example that everyone cares about. Wait, did I? Oh, never mind. Okay. Oh, because there's another result that I want to talk about. So I need to do a very quick detour to commutative algebra. So I want to introduce the concept of a Noetherian ring. So as you see, the name is from Emmy Noether. So I stated 2 equivalent definitions, but for now, to be quick, we just think of it that a Noetherian ring is a ring whose ideals are all finitely generated. So meaning that any ideal of this ring, of a Noetherian ring, you can just find a finite set of generators and it generates the whole ideal. Okay. So because I'll state 2 key results were not proof. So there's a key result called Hilbert basis theorem. So it says that if R is a Noetherian ring, then the polynomial ring Rx is also a Noetherian ring. So meaning that you see all the polynomial rings we've done here, all the ideals here, it turns out that they're all finitely generated. For example, this one was finitely generated, but that's a stupid example, but you get the idea. Okay, so this is and it's not only in one variable. So if you recall in abstract algebra 1, so you can even prove that polynomial rings over a Noetherian ring in any number of variables is also Noetherian. It's by just using the concept that you can adjoin, remember adjoining elements to a ring, that section, remember that? So it all comes from the idea that when you adjoin n things into a ring, you can adjoin them one at a time. That's all you're using. So meaning that you can treat this as, so it's kind of an induction argument actually. So we start with one variable, right? Start with one variable. So you adjoin, so Rx1, x2, you can just look at it as Rx1 adjoin x2. So it's polynomials, can think of it as polynomials in x2 with coefficients that are polynomials in x1. And so on. Okay? And because this is Noetherian, so by the first part, this is Noetherian. Then you keep adjoining. So that's the induction argument. Okay, keep adjoining one at a time, you get for n polynomial rings over n variables. It's Noetherian. Okay. Okay, so the key result I want to share here is, I don't know if I should call it a theorem or proposition, but I'm not really bothered. Okay, so if A is an algebraic set, if we have an algebraic set, maybe let me say in this way. Any affine algebraic set is the zero set of finitely many polynomials. Meaning that, let's say now you're considering the zero set of an infinite number of polynomials. So because polynomial rings are Noetherian, this means that you can somehow throw away extra polynomials until you get a finite set, and and you don't lose any zeros. So that's the idea. Okay. Yeah. Yeah. Algebraically closed field. The proof for Hilbert basis theorem is a bit involved, so yeah. Oh, you mean? Okay. Actually, why is it a result of Hilbert basis theorem? That's your question. ideal has a do you need that? Assume, because algebraic set already means there is a zero set, right?
Yeah.
Yeah.
You say algebraic set is zero set.
Yeah.
Then if you want this result, then means your
Yeah, so it's a stronger condition than the definition. Yeah.
idea of the thing is generated by the subset of the polynomial. Then your zero set of the
Ideal. You are talking about this one, right? We're talking about this part too. Then
you can write down that if A is the idea of the kx1 to kxn generated by T is a subset.
My A is a subset of affine space.
I mean, small a, small a ideal. If you want to use the Hilbert
Yeah.
basis theorem.
Yeah.
So if you want to use the
Yeah, we assume that in the proof, but to state the result, we don't need to state that. Yeah. No, because as in, why is it? Why does it keep turning off? As in because our set is algebraic, so you can find some polynomial set such that let's call this set A. Let's call this set A. So because it's algebraic, so there exists some set T such that A is VS, right? Yeah, so I know, yeah, then you just take, so it's part of the proof actually. So and then this is equal to, by the proposition result, is equal to VT, where T is the ideal generated by S. So it's not a condition. The condition is just algebraic set. Yeah, T is an ideal. S may not be an ideal, but yeah. So you have to, yeah. I guess what you mean is that we need to, in the proof, we need to somehow convert this S, because S may not be an ideal. So we somehow need to convert it to be an ideal and use the fact that T is finitely generated. You can still take the ideal of it. Because the ideal generated by that infinite set is still contains any multiples of things in that.
That VS is expressed as finite remaining polynomial series.
Yeah. Okay. So far up to here, everything makes sense, right? Up to here it makes sense, right? So, okay. So VS equals VT comes from part 2 just now. Comes from this. So that means the zero set of any set of polynomial is the zero set of the ideal generated by those polynomials. So this is what we mentioned just now. So we're using it here. We use it here. Yeah. Yeah. S can be anything. We just know that because it's A is an algebraic set, we can find such an S. Yeah. Yeah, ideal generated by S means this ideal contains all multiples of things in S. Yeah, finite. Yeah, finite linear combinations. Is that the correct word? Yeah, not really linear, right? Yeah. Finite sums of multiples of polynomials in S. We should say it that way. Yeah. Yeah, that's the next step, and it's one line. So now we have A equals BT. So now we can say that use Hilbert basis theorem. Is because our K x1 through xn is Noetherian. So our T here is a subset of our polynomial ring, right? Let's say we are affine n space here. Okay. So this is an ideal in this polynomial ring. And Hilbert basis theorem says this polynomial ring is Noetherian. So for a Noetherian ring, every ideal is finitely generated. So T is finitely generated. Yeah. So you get idea. You see how we link it together. So actually we finished the proof already. We still want to skip the proof, but we turned out to sketch the proof. Not even a sketch, it's a proper proof. I just didn't write it back properly. Okay. Okay, so now this is finitely generated by Hilbert basis theorem. Okay, so in particular, so meaning that you can say T is generated by some F1 through Fk, right? That's what finitely generated means. So, and then you know, so in our it means that in some sense this is like our, let's say our S prime are these K polynomials. If you want to really like write out the proof formally, this is the way to write it out. Is by Hilbert basis theorem, because our polynomial ring is Noetherian, so we can apply Hilbert basis theorem. Yeah.
So it's from the definition of
This is one of the definitions of Noetherian, and then Hilbert basis theorem says that polynomial rings over Noetherian rings with polynomials with coefficients in a Noetherian ring is also a Noetherian ring. Yeah. I mean, yeah. Yeah, I should say that. Okay. So I'll state a general result here. So, example. I want to be a bit more general. Every principal ideal domain, or you might know hear this as PID. So any PID is Noetherian. It's very obvious, right? Because PID means every ideal is principal. Every ideal principal means it's generated by one element. So it's finitely generated. Finitely generated by one element. So this is a very trivial observation. And then as you mentioned, fields are PIDs. If you can remember that from your algebra class. So yeah, I should mention that. So that's why. So because K is a field, so it's Noetherian. So polynomials over K are also Noetherian. So their ideals are finitely generated. Okay, so just to complete the proof formally, so finite generator, so you can list out a finite list of generators. So and then you can define say S prime, because I want to distinguish it with that original S. I give it a different name. So I let S prime to be these K polynomials. And then again, by that proposition just now, Vt is equal to Vs prime, right? So we found our set of finitely many polynomials S prime. Okay, just to complete the argument. And this is the result that we need to use to explain what are the algebraic sets in A1. Okay. Okay, so now, never mind. So let's talk about algebraic sets of A1 over complex numbers. Okay. So first observation is that if let's say we take any polynomials, any set of polynomials in one variable, because we're in A1, so Cx. Any set of polynomials. So then again we use that part too. So Vs is V of the ideal generated by S, right? And then now Cx is in fact a PID. So the ideal generated by S is generated by one element, say F. Because Cx is a PID. Okay? So it's in fact, it's a abuse of notation. So we can just say it's the zero of the polynomial F, right? Okay? So now, maybe I shouldn't take this first. Maybe I should do something like. Okay, so let me see how. So this means that if A is any, if A is an affine algebraic set, then A is Vs for some S, right? So maybe I should just write it like that. So we can proceed with the argument just now. So because Cx is a PID, so any ideal is principal, assume that it's generated by F for some F in Cx. And then, so you can write this argument out. So meaning that, so we have just shown that any algebraic set in A1 is the zero set of a single polynomial. Okay, so that's part one. Okay, so we have found the general form of an algebraic set in A1. Is the zero set of exactly, we can write it as the zero set of exactly one polynomial. Okay, so that's one part of the argument. Then, okay, now we want to be a bit more specific. So let's say the degree of F is let's call it, let's say the degree is K. Okay. Then again, because we're over complex numbers, so you can always write this polynomial f as a product of linear factors, right? This is the, so you can write it as like x minus alpha 1 through x minus alpha k, with some leading coefficient. I forgot about that. Let's say, let's call it A. For some A alpha I in complex numbers. Okay. So so this means what? So this means I'm still confused with my notation. So this means that because of the fundamental theorem of algebra, the zero set of f is always non-empty because we're over complex numbers. So f always has a root. So Vf is always non-empty. Okay, so actually in particular, you can write out Vf explicitly, right? With this factorization. So our Vf is basically our alphas, right? So this is, so we have just shown what Dr. Yan said half an hour ago. So this means that we have concluded that any non-empty algebraic set in A1C is finite. It's a set containing just finitely many points. Yeah. Yeah, that's why I mentioned it. That's why I haven't mentioned. So that observation is coming. So we haven't even mentioned this so far, right? Is the empty set algebraic in general? Any ideas? So you just treat it as the zero set of the whole ring, right? So the whole ring is it's quite when CX, right? So actually this holds for any field, any polynomial ring. Okay? Because you want to find a common root of whatever polynomial you can think of. So there's nothing, right? That's all. So this is a rather trivial observation. So, and then the next thing is, what about the whole space? What about the whole space? The set of all complex numbers. Is it a zero set? Is it an algebraic set? Can you think of it? Can you think of a polynomial that has all complex numbers as a zero? Yep. So it's V of 0 basically. So this 0 is the zero polynomial. Okay. So maybe to put Dr. Yan's words properly, we should say that any proper algebraic subset of A1 is a finite set. So yeah. Wait, let me see. part one, the argument for part one holds, always holds. Or mean this line, yeah. Yeah, I should add the word proper. Where is it?
The part actually should get the diversity topology because we still need to consider our MGZ and whole space in the topology.
Yeah, that's why I will leave that for next week. I just noticed we forgot about break. So and it's 8:45. So I think I think it's a good time for a break. Okay, break for 10 minutes. I thought it ends at 9. so
Then can you like give me a feedback?
I don't understand why India were very we're not so much to like.
Yeah, but
There were two metrics in India. And
现在我应该非常不脏，应该不能。
talking about how you actually
哦，原来是都是男人。
they would usually
smallest idea of the idea is much more
那时候哈秀，那的哈秀呢？上来又要讲韩式，
有注意到我会跳吗？
我知道你很像，很想避免了，但是我现在又很像很难避免。
所以基本上我已经偷偷讲了，
已经偷偷讲，
我已经偷偷讲了，我已经偷偷讲了。
这样你把one variable 都讲完了，哎，连 n variable 只是说着讲话了，就没有聊。
你不是个零分。等一下要讲 ideal 了，应该是讲 ideal 了。
ideal polynomial
啊，就是 I 咯
，I 啦，
的方特 I 啦，
完了，
的方特，你又不是不懂。
不是，我不懂啊，立马先生的你。This is just
没有啦，看错我的。
So we first
我不会注重了。
category of ring of polynomial and category of 什么 algebraic。
你看我这里都说我特地分出来写的。
啊，真的啊，这不是。
Then just to complete argument。我人力是写2行，我又手写，我当然不抄了，所以我就 讲的话，哇，你讲的东西真的是不需要maintain的吗？
哪一个？
你刚刚讲的那个东西，它直接看 from algebraic，它是
我记得他说是有 mention 的，
嗯，
他说是有 mention 的。
就是不管什么 set，你都把它 convert 成 ideal 来拿 ideal 绝对把那个 set。
所以你要做那个 assumption。
没有不用 assume 的，那个一开始的 set 就 exist 了 ，because 它是 algebraic set，所以它是 zero set of subset。
If
zero subset。
the idea is generated by T，
Yeah，
所以他可以 assume 了，他 assume 了，他才你可以再继续这样做下去。
不是，他这行就是我那个 proposition 的，所以你有看到我怎样重新整理这个 part？
你是说
我那次是重新自己整理过这一段的。
哦，所以你是已经把那个 assumption 这个 statement 已经特地分出来讲，然后这边再带下来。
我觉得这样子比较顺。
是有一些人就没看到那 condition 就怪怪了。你可以讲 under 上面的，
他不需要嘛，他只是讲，他主要是要讲这个嘛，就是这行的。
对，但是你要有这个啊，要有这个他才有这个。
对呀，对啊，说我 apply 的时候，我不需要 assume 这个啊，我只要有 T 就可以了嘛。我有 T 我就借哪 ideal 绝对by T。
但是，只是说他前面还是要背上这个条件，只是说有些人没有看到
有条件吗？没有条件啊。
If A is generated by E， 这个是啊，
来了，就是我写在这边吗？我写在这边吗？
那
我写在，我写在这边吗？
哦，if， 只是这里看不出来了，
Yeah.
就我们不懂哪一个条件，哪一个。
我已经 error 了嘛，不用 if 了。
你就讲under the hypothesis of two 了，OK， 这样好。
好了，我刚才是讲 part two 了。
part two 不我说 part two， 但是 hypothesis of two。
所以你在讲的就是我这个 statement two 了。
我只是
你
直接就我会
确实，因为我他就在拖引擎在那边，
还是长的。我能找到就是把挖出来。
像那个这个原本的书是在你们
Just Mills 那本
Mill 的
这是不是谷歌一下就有了？
谷歌者 Algebraic Geometry JS Mill 就 MILNE。但是我 end up at least 我的 part 我没有怎么跟
大同小异了。
你打 MILNE 就可以。
你应该不用在 Z library 啦，用谷歌就可以了。它歌还有自己的 personal，
还在有上去。MILNE。
我看到我然后你觉得比如说会拿出来，拿起来，你们是吧？那就不用拿出来。我觉得在你身上， 不知道谁生一本出来。如果还我所以来，不要时间上不够。第一个 PI 在一起可以一定有那其实他有可能。就他讲 PI 是不是可能是你喜欢 Algebraic， 他们不是懂的。因为有的，他怎么说？一结束又给他搞到标准的时候，就是全部那个表格。Yeah.
So is everyone back? The break is ending. If anyone wants to join the team, we have the early access barcode link. It's either in Insta or email. If you want to join the teams, you can fill in the form, and Rachel will take care of everything. Okay.
Or you can just find me now. 3 million. Okay, so behind schedule. Okay, so the next section. Now we want to talk about what is the ideal of an usually we really only care about algebraic sets, but let's talk about subspace of affine space in general. So meaning that for any subset of AN, we can associate an ideal, associate to this set an ideal of the polynomial rings in n variables. So that's the agenda for our second half. Okay, so Immediately, new language, new definition. So we just pick any, let A be any affine set of AN. Okay, so we call it the ideal of A. Is there a better name for this, by the way? So I see quite many books, they just call it ideal of A in the polynomial ring. And we denote it by, so for zero sets, we use the word V for vanishing or variety. Variety stands for algebraic variety, which we'll talk about next week. So, okay, so now we talk about IA, the ideal of A. Okay, so it's the ideal in that polynomial ring, as we say. So what ideal is this? It's actually, I should say it's yeah, I think let's do it very like that. Let's do it like that. So the set, IA, which is basically the set of all polynomials that have A as their zeros. Okay, so where such that f of x is 0 for all x in A. Okay, so it turns out that this set is an ideal in the polynomial ring. And we just call it the ideal of A in that ring, in the point. Okay. So you have a feel for this object. So this set is the set of all polynomials that Q all points in A. Okay. So again, let's look at examples. So I didn't prepare any example here. So let's see. Okay. Okay, let's just look at the set A. Let's try to work this out on the spot together. So let's say A is the set minus 1, 1 in CX. No, not CX, A1. So what is IA? We certainly cannot list everything, right? Because there are already infinitely many of them, right? Because you can think of x squared minus 1, right? So it must contain x squared minus 1, right? Because both minus 1 and 1 are zeros of this polynomial. Then what else does it contain? Any multiple of x squared minus 1. Right? So in fact, so it must contain x squared minus 1, and it can contain any multiple of x squared minus 1. So it's basically the ideal generated by x squared minus 1. In this case, it's a bit easier. Correct? I just work it on the spot. Yeah. So you have a feel for what this ideal is. Okay, so okay, so we do the same process. like just now we talk about properties of zero set. Now we want to talk about the properties of this ideal. Okay. So yeah. 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 IA mean is how should I answer this? Because by definition it has to contain all polynomials that kill all the points in A. So you have to include all of them. Are there more than one way to include all of them? Yeah.
Why the idea is contained, why I of A contained in the experiment one?
Which one? Or you're talking about the general case or the example? Yeah. The idea here is that in this case it's a bit easier because when you see -1, you definitely think of, I mean, we skip a bit, but when you see -1, you definitely think of x plus 1, right? Right? We start like that, we start guessing like that. Right? Then if you want to include 1, we definitely think of x minus 1, right? We're over complex numbers. So you can definitely find a degree 1 polynomial having that as a root, right? So it's just x minus that. Right? So these two must be in the ideal, right? So, yeah, I said, yeah, not quite.
Whenever you have something with minus 1 and 1, it must be divisible by x plus 1 and divisible by x minus 1. So because you have unique factorization, it must be divisible by x plus 1 times x minus 1. So
yeah,
divisible by
so it's correct actually. Yeah. So I mean, I'm just saying that if we do the guessing like that, I'm tempted to write it as like it's any multiple of that two polynomials, right? So it's generated by these two polynomials. Okay, can I say that? Okay. I get it. Okay. Or maybe let's argue this formally. So meaning that so we claim that IA is the ideal generated by x plus 1 times x minus 1. Right. So we claim this. So now this is a legit abstract algebra 1 assignment. So how do you do this assignment if you're taking that course? So you show that one side is a subset of the other, right? So one direction is easy, which is basically what I just said, because x plus 1 and x minus 1 must be in the ideal. Their product must be in the ideal. So it has at least one of these elements. So any multiple of that also has the same 0. So this ideal is a subset of this. That's one direction. So the more complicated part is the other direction, which actually Dr. Lien already mentioned. So let's write it out. So the easy direction is this one. So the I should say, x plus 1, x minus 1 is in must be in IA by definition, by the definition of IA. Because IA contains all polynomials that has -1 and 1 as their zeros. So by a very easy observation, x squared minus 1 is one of them. So it must be one of the elements, right? So this is what this line is saying. So meaning that any multiple of that is also in IA, right? For all f in CX, right? Yeah, so that's one direction. So now the more complicated direction is that we want to show that IA is a subset of the other one. So now we have to take any random f in IA, right? Then by definition of IA again, f of x must be 0, right? But then f of 1 and f of -1 are both 0, right? So you don't even need extra algebra, you just need 101, right? So by factor, you can say by factor theorem. So it means that x plus 1 and x minus 1 both divide f of x, right? I think this argument even the year ones can follow, right? Okay, so meaning that we can write f of x equals x plus 1 times x minus 1 times some quotient, right? For some polynomial q in CX, right? So multiples, so this is a multiple of x plus 1 times x minus 1. So it's in the ideal generated by that, right? Proof that. Everything makes sense so far? Any questions? Okay. Okay, so now let's list the properties. So again, we have, just like zero sets, we actually have an inclusion reversing property. Meaning that if we have A and B affine sets, contain in one another, then what are their ideals? Then their ideals split. The containment of their ideals split. Just like zero sets. Okay, so what's the intuition for this? Without going through the proof. So this means that okay, so now you want to find, again, it's like, just think of who's big, who's small, and how to fulfill a bigger audience, how to fulfill a smaller audience, that kind of intuition, same thing. Okay, so now B is the bigger set. So how many polynomials have more zeros? Just think of it like that. So less polynomials have more common zeros. Eh, am I correct? Yeah, less polynomials have more common zeros. That's all. Same intuition. Okay. Okay, now.
What?
Yeah. More, okay, key thing to say, more polynomials means more conditions. So it means that when you have more conditions for your boyfriend or girlfriend, you have less choices. Yeah, that's a good way. That's a good way of putting it, yeah. You should have mentioned that 1 hour ago, I guess. Yeah. Okay, now part 2 is that, again, if A is a subset of B in affine space, then what is the ideal of the union? Any good guess? Can you split this up into IA and IB? Any good idea? Any good guess? So think of it, what is A union B? So again, A union B is what? Putting the zeros together, right? Kind of putting the zeros together. Kind of idea. So okay, put all the zeros together and you take the ideal. So you want to find all polynomials that vanish on A union B. What polynomials vanish on the union? This is probably this is not so straightforward. The proof is not very long also. Never mind. Okay, the answer is intersection. Yeah. So because this doesn't hold in general, it only holds for this special case. Is it? Is it? Is any A and B? I forgot. Or did I have a typo in my notes? I forgot. Okay, probably it's a typo. Okay. I find this a bit more difficult to explain intuitively. Yeah. Yeah.
So if you are an I of A and I of B.
I of A. You vanish on the union, then it must vanish on polynomials on both sides. Yeah. Okay. Does everyone else get it? Yeah. Okay. Yeah, actually, yeah. This quite a number of these are set theoretic. Okay. Where am I now? Okay, there's one. Okay, so now we're doing a bit fancy. So I claim that any set is a subset of the zero set of its ideal. Is this obvious? This obvious. It's obvious. So you take you collect all polynomials. You collect all polynomials that vanish on A. Take the zero set. So it must contain A. That's all right. That's how I think. Is it very obvious? Intuitively. Okay, so good question. I haven't thought of that actually. Why is it not equal in general?
Arbitrary A, A could be something stupid like, let's say, rational numbers, complex numbers. It would be the smallest algebraic set. If you do B and I, then it's going to be the smallest algebraic set containing A. But A might be not algebraic itself. So like, take A being the right one.
So meaning that if A is algebraic, then equality holds.
Yeah, but
It's basically the Nullstellensatz, right? Yeah. Okay. Okay, so let me mention one more thing. Then we're almost reaching the Nullstellensatz. And almost time's up. Okay, okay, and then now we do it the other way around. It's actually kind of a complement to that. So what is exactly V of IA? Turns out to be the never mind. I think I should not. I think I'll skip this one. I want to mention it's the closure of A, but we need the Zariski topology for that. So let's keep that next week. Okay, so for now, I can only talk about these three. First, there's one more that we need, but before that, I have to tell you a new object again. So, meaning, what is so let's say, so let J be an ideal of a ring R with unity. So the experts will know what I want to talk about now already. So I want to introduce what is the radical of J. So we denote it as rad J, or some books actually write square root J, depending on what you like. So this contains everything of the form it contains everything in the ring. So everything in the ring such that some power of it is in J. Is it Z, right? Yeah. Z or N? I forgot. Oh yeah, ring may not have inverse. Okay. Yeah. So the radical of an ideal is basically it contains all elements of the ring such that some power of it is in that ideal. Okay? So that's the way to feel this object. And then now I want to introduce that J is called a radical ideal if its radical equals itself. Okay, so radical ideal is an ideal whose radical equals itself. That's all. Okay, so this turns out to be the key type of ideal to do algebraic geometry, to convert geometry into algebra side. So on the geometry side is the zero sets. On the algebra side, later we see it turns out to be this type of ideals. Ideals whose radical equals itself. Okay, so that's why we need this. We need this definition. So now we can talk about one more property. Is that if J is an ideal, in algebraic geometry, we like to denote ideals by lowercase fractal letters, right? But I don't know how to write that in handwriting, so I'm just trying to use some more standard symbols. It's an ideal in the polynomial ring. Then now, so just now we did V of IA. Right? So now to talk about what is I of Vj. So actually, this is one version of Hilbert Nullstellensatz. So it's equal to the radical of J. So this is the strong version. This is basically the strong Hilbert Nullstellensatz. We'll state it right after this. So basically, once we compile all of these data together, we can arrive in this big theorem. Which is that now we're finally ending with the keyword of today's title, right? Hilbert's Nullstellensatz. Obviously German. We'll mention what it means in a while. So it turns out that we have there is a inclusion reversing bijective correspondence. Bijective, just to remind you, it means one-to-one. Between affine algebraic sets, so meaning zero sets, in some way, in AN, and radical ideals in polynomial ring in n variables. So the n is very important here. Okay. So basically, after all the struggle, this is the key result that we want. Okay, so one-to-one correspondence between radical ideals in the polynomial ring and algebraic sets. Okay, so if you want the map explicitly, so we have an algebraic set A. So what ideal can you map it to? IA, right? That's what you learn. Then if we have a radical ideal J, what can we do? Let's take the zero set. just take the zero set. Right? So that's what we've just done. Okay. So meaning that to study the zero set of a polynomial, we study the ideal in the polynomial ring. That kind of thing. Okay. Okay. Looks like it's time's up. So should we stop here or should we just do a couple of examples? Or it's 9:30. Yeah. Do you want to extend? We can just do a couple of examples. Yeah. Okay. So, but basically, so this is the goal that we wanted to establish for today's session, is to show how you can convert between problems in algebra, which is the right-hand side, the ideal side, and problems in geometry, which is the zero set side. Okay, so that's where, in some ways, that's how the area of algebraic geometry really got going, really exploded. Because of this formulation. And including next week's session, we talk about Zariski topology. So Oscar Zariski was the one who made all these things formal. Okay, so the takeaway of today is algebraic geometry. Right? Okay, so that's the key for today. Yeah. Yeah.
So basically, I gave a challenge for picture in every point. This is the algebraic geometry. So that must be a
Wait, what? What is that? Stuff, right?
Well, we have one stupid picture containing 2 points. Okay. Okay, so what is, so here S is not an ideal. So by our proposition now, this is equal to V of the ideal generated by S. Right. So what's the ideal generated by S? So ideal generated by S is the principal ideal generated by x squared minus 1. So now the question is x squared minus 1 a radical ideal? So okay, so we want to show that the radical of the ideal generated by x squared minus 1 is equal to itself. That's what we want to prove. So again, set theoretic proof, prove 2 inclusions in both directions. So I haven't tried this proof actually. So yeah. So we don't need to do it in class. So okay, so homework. Okay, so that this ideal is a radical ideal in CX. Yeah, so these are the types of homework you do in abstract algebra class, right? Okay, so maybe next week turns out that supposed to be another speaker, but somehow I have to cover it, so you'll see me again for one more session next Tuesday, not Thursday. Okay. So probably let's end there today. We'll continue with a bit more examples on the Nullstellensatz, and then we'll start to do Zariski topology. Okay. So that's all for today.
For anyone coming next week, remember that it's Tuesday, and for the rest is the same Thursday. Okay, only for next week is Tuesday. Same time, same place. Okay.
Yeah. Stop. Stop. 那个
recording 是 Rachel 的
哦，是 Rachel 哈。
Rachel record. Yeah.
Why to show my